Today we're going to be talking about geometric isomers. In a previous lesson, we've talked about structural isomers, which are compounds that have the same molecular formula, but their structures differ in terms of where the carbons are placed. Geometric isomers differ only in the arrangement of their atoms in space. In order to have a geometric isomer, you must have a double bond between two carbons, and the way that the subgroups are situated across the double bond determines the type of geometric isomer that you have. In this example here, you will see that we have an alkane. It is 1,2-dichloroethane. And notice that with single bonds, they can easily rotate. What appears to be a different structure in an alkane actually is not. Due to the way the structures are written out, they are actually the same. When you have a double covalent bond, so a double bond between two carbons, you're going to notice that the rotation around that double bond is fairly restricted. So the molecule ends up appearing to have almost like a top and a bottom, and the angle would be around 120 degrees, but there's a restricted rotation. Let's take a look here. So you can see here that single bonds have free rotation. So no matter which way you turn them, it'll end up being the same molecule. Double bonds and cyclos have restricted rotation. So you can see with the alkenes, it is a planar molecule, meaning it has sort of like a top and bottom. If we had molecule kits available to us, I would want us to build these two structures. Notice that we have 4 carbons, and I have a double bond between carbon 2 and carbon 3. Notice that the methyl groups are situated somewhat differently, and same with the hydrogens in example A and B. Let's take a look, and I will build these with you using a molecule kit. So if I was to construct this particular alkene, this would be some sort of butene. And because the double bond is at carbon number 2 position, it's 2-butene or but-2ene. Notice that the methyl groups appear to both be on the top and the hydrogens are both on the bottom. So we look at where the double bond is and we decide where those hydrogens are situated. In this scenario, we have the hydrogens across from one another, across the double bond. So this is known as a trans alkene. So this would be trans 2-butene. Now let's put the methyl groups both on the same side and the hydrogens on the same side. This is referred to as a cis alkene. And so this would be cis 2-butene or cis but-2ene. Whenever you have the hydrogens on the same side, it is known as cis. Cis meaning same. So if I go back and I move this to a trans alkene, you're going to notice that each carbon has 2 different functional groups attached to it. So we're looking specifically at where that double bond is. And so when they're across from one another, we call that trans. So as we saw in the video, we noticed that at carbon 2 and 3, there was a double bond. There was limited rotation, and in order for us to recreate figure B, we would have to break the bonds. And in order to break those bonds, that requires a certain amount of energy to do that. And in this case, 270 kilojoules per mole. So there's insufficient energy available at room temperature in order for that to happen on its own. So as we saw, if we were to actually draw the structural diagram, we would number the carbons 1, 2, 3, 4, as you see here. 1, 2, 3, 4. Notice that this gives us more of sort of a U shape. This one here is a little bit more linear. We take a look at the hydrogens, and we take a look at what appears to be methyl groups, but really they're part of the parent chain. And we see that each carbon has 2 different groups on them. So this is some sort of geometric isomer. Because these hydrogens are on the same side, we call that a cis alkene. And because these hydrogens are across from one another where that double bond is taking place, and what appears to be as methyl groups are across from one another, that is called a trans alkene. Whenever you have cis and trans isomers, what ends up happening is their melting points, their density, all of their physical and chemical properties are different. So they are different compounds and they would be used for different uses. So we have to distinguish cis and trans. We can't just call them both 2-butene because their properties are different. Here is example number 2, where you can have things other than those methyl groups. In this case, we have chlorines as our subgroups across from one another in a double bond or on the same side. So in the first example here, you have a cis 1,2 dichloroethene. And in the second example, you have the trans 1,2 dichloroethene. So again, we take a look at where that double bond is located. We take a look at where the chlorines are from one another, where the hydrogens are. Are they across or are they on the same side? And again, this chart just illustrates that the cis and trans isomers are different molecules with different properties, different densities, melting points, and boiling points. This model that they're depicting here is called a space filling model. Okay, so how that would look. So let's take a look. When we are looking at alkenes, we have to determine, do we actually have a geometric isomer? So you want to take a look at each carbon individually where the double bond is located. And then does each carbon have 2 different functional groups? Yes. And so that indicates that you will have a geometric isomer. Let's take a look here. This carbon, does it have 2 different functional groups? No, it both has chlorine and chlorine, so that is the same attached. Same with here, these are the same, so you cannot have a geometric isomer in this case here. Again, let's take a look at this example number 3. This carbon has 2 similar functional groups. This one has 2 different. Both the carbons that are taking part in the double bond must each have different functional groups in order to be qualified as a geometric isomer. And the last one, does this carbon here have 2 different functional groups? Yes, it does. So does this carbon. So this is considered to be a geometric isomer. Let's take a look at this example here. Would these be cis or trans or neither? So in example number 1, does each carbon that takes part in the double bond have different functional group? Yes, it does. So this would be a geometric isomer. Now we have to decide, is it cis or trans? Well, if we see where the hydrogens are situated, they are on the same side. These guys are on the same side, so this would be a cis. Here, we have hydrogens across from one another, different functional groups. This would be trans. Okay, and in this example here, we've got hydrogens on the same side, 2 different functional groups on each carbon. This is a cis, and in this example here, we have trans. Okay, let's give this one a try. This certainly looks like a planar molecule the way that it's been drawn out. I noticed that this carbon and this carbon both have different functional groups, so it is in fact a geometric isomer. Hydrogens are on the same side, so let's take a look. Cis-2 pentene it is. This one here. Does this carbon have 2 different functional groups? No, it does not. So automatically, this cannot be a geometric isomer. So how would we name this? We would name it like we normally would. 1, 2, 3, 4, 5. So we have 5 carbons in a row. The double bond is at carbon number 1. So this would just be named 1-pentene. Last example, we've got 1, 2, 3, 4, 5. This is some sort of pentene again. It is at carbon number 2, so it's a 2-pentene. Now, do I need to put trans or cis? Yes, I do, because the hydrogens are across from one another. So this would be trans 2-pentene, or you could also name this as trans pent 2-ene. Now that we've done a lesson on geometric isomers, I'd like you to go through and do this worksheet just for practice. Couple of things to go through with you. So in this first example, they want you to take a look at this structure, and then they want you to draw it in its cis isomer form and its trans isomer form using the condensed structures. So what you'll do is you'll make note here when you go to number this chain, 1, 2, 3, 4, 5. We've got pentene, and because the double bond is at carbon 2, this is 2-pentene. What I do is I start off with where the double bond is. So I'm going to draw those two carbons. And then what I'm going to do is I'm going to draw everything so that it is a planar molecule so that there's top and bottom. So what I want to do is I want to leave these hydrogens here so that they are on the same side. So I will go ahead and do that. And then this methyl group that is attached, I will have that come down and I will write that as CH3. And then on this side, I have a CH2 and a CH3, which appears to be like an ethyl group. And there you have the cis structure. So when I go to name this, you would do cis 2, and we said this was pentene. Okay, and you can go ahead and draw the trans version as well as naming it. In question number 2, what they're wanting you to do is to name it, and if you need to include a cis or a trans where appropriate. So remember, what you want to do is you want to take a look at the carbons where the double bond is located, and if you have 2 different atoms or functional groups attached to each carbon that is partaking in the double bond, then you in fact have a geometric isomer. In this case, because this carbon has 2 hydrogens attached, it's not 2 different atoms, this is not a geometric isomer. So you would just name it like you normally would. So in this case, you've got 5 carbons, so this would just be 1 pentene. So you're going to go through and do that for each of them. The hint that I always find is if you see that it is drawn so that it looks planar, as if it's a top and bottom, most likely in that case, you do have a cis or a trans, okay? When you are looking at the line diagrams, if you are struggling with that, what you can do is wherever there is a point, you can go ahead and put in a carbon, okay? So you'll know that in this case, you've got 1, 2, 3, 4, 5, 6, 7. So you have some sort of heptene. Remember, you're going to number the chain so that the double bond is coming off at the lowest possible number. So in this case, you would be going from left to right. So we've got 3 heptene. Now, is this in fact a cis or a trans? Well, what you would do is you would say, okay, this carbon needs 3 hydrogens, this one needs 2. This carbon needs 1 hydrogen, so does this one. So I noticed that here we're getting that sort of U shape. We're getting that planar molecule. So in this case, you do have a cis isomer with both hydrogens on the same side and the other atoms or groups on the other side. When you are asked to draw the line, skeletal, and condensed versions, what I like to do is I like to start off with the parent chain first. So I'm going to do that sort of rough up here. So we've got 3 hexene. So what I'm going to do is I'm going to draw 6 carbons in a row. 1, 2, 3, 4, 5, and 6. At carbon number 3, I will put a double bond. So I've got something rough here, and I know that at carbon number 2, there would be a methyl group. So I'll put that like that, and I'll put in the hydrogens as needed. Now, this is my structure where you can't tell whether it is cis or trans. In this case, they want a cis. So what I'm going to do is I'm going to take this, draw the double bonded carbons first, okay? So I've looked after this part. And then what I'm going to do is I'm going to keep those hydrogens on the same side and then drop everything else so that it's below or in the same plane. You could have put both hydrogens on the bottom and then had these groups on the top. It doesn't really matter. Okay, and we also have, remember, that methyl group coming off of that carbon there. And then here we would have those. Now I can draw in the hydrogens, or I'm just putting in the dashes for now to represent those hydrogens. What would the line structure look like? Well, what you would do is just as they've done up here, you would start off with your carbons. So, and then you would put a line to represent that double bond. And then we see here, I'm going to indicate, and I'll use this as the bottom one, that ethyl group, and you want to just sort of bend it, okay? And then on this side, you've got sort of like another ethyl group, okay? And then a methyl group coming off, okay? So this is what the line structure would be. Okay, and then the condensed structure, I'm sort of not putting these in the right spot. That's just where you would do your hydrogens, okay? And then instead of writing the dashes, you would write CH, and that's linked to a CH3, which is linked to another CH3. And over here, you would have a CH2 linked to another CH3. As long as you can do this structure and this structure, we're good with that, okay? So give those a try and then check your answers after you've done the entire front and back, or page 1 and page 2, and see how you did.